Alright, so what we're going to do today is we're going to do the last two of the big tests, the root test and the integral test. Some of you may be able to notice, maybe we'll have a nice panoramic view of,
Oh.
Nice there. To some of the constructions being done, high technology can move it up and down. So the question is, if I give you a bunch of dominoes, what is the best overhang you can have? And again, I was deliberately vague in the way I gave you the rules. Too many times people interpret and force additional rules than were given. And so a lot of people assume that you have to have all of them facing in the same direction, and you have to basically just keep moving them out like this. Interestingly, if you do it like this, the best you can do is the harmonic numbers. So what that means is, I don't know if this is viewable here, but you start off with the first one here. The next one you put over halfway. The one after that you put over a third, a fourth, a fifth, a sixth, a seventh. And if you're just going to go in a straight line like that, the best overhang you can get with n dominoes is the sum of the first n reciprocals of the positive integers. And so then the question becomes, well, can you do better? And I am not a big fan of Stalin, but every now and then they do say something good. Sometimes you take one step backwards to take two steps forward. And so a really good system, I'm not sure this will be visible, I might just have to hold it, is something like this, where you can get a really large overhang by almost making like a little sandwich like this, and then you're putting like a big window over here. And so amazingly, you can do significantly better than the sum of the first n reciprocals. So if you just do the standard one, going like this, you get the sum of 1 plus 1 half plus 1 third plus 1 fourth all the way up to 1 over n, which we'll see in a few minutes is about log of n. You can get some power of n, I forget if it's n to the 1/3 or n to the 1/2, significantly greater than log of n. And the reason I want to talk about this is because it's so easy to go through life with blinders on and additional assumptions that are not really there. To just think, I've got to attack the problem this way. And again, a lot of times you get accused of being a smartass and you get into trouble. I don't mind if this is being recorded. I've told several of you that they wrote the writing intensive requirement at Williams College incorrectly. It says, I'll stop there. I'll just leave it for you to go and read the writing intensive requirement. There is a mistake the way it's written. You can sometimes get away with things like this. And again, it's really good to have a fresh perspective when you're looking at things. Don't force yourself to do things the way everything else has already been done. Alright, so let's do the root test quickly. So again, an will be a sequence of positive numbers. Let rho equal the limit as n goes to infinity of an to the 1 over n if it exists. If rho is less than 1, what do you think will happen? What would you guess? So you should know this, you should be prepared, you should have read all the root test. So if rho is less than 1, then the sum, n goes from 1 to infinity, of an should converge. If rho is greater than 1, then the series diverges. And if rho equals 1,
no information.
No information. Okay. So again, the root test should only be used after you do other simple things. Do the terms tend to 0? If the terms are not tending to 0, there's no need to go to the root test. Okay? But if the terms are tending to 0, then the root test is another nice one to look at. So this requires you to be able to take the nth root of a number. What would be a good series to try this on? What would be a good one to test it with? Do we know anything that converges or diverges? Yes?
Just 1 over n.
1 over n. So example, let's try an equals 1 over n. We've been talking about this for a while. We do have a proof that the sum diverges, but the proof required us to be very clever. Alright, so let's look at the limit as n goes to infinity of an to the 1 over n. This is the limit as n goes to infinity of 1 over n to the 1 over n. This is a little bit hard to just look at and evaluate. Okay? So the question is, how do we handle something like this? The numerator is no problem, but I've got an n to the 1 over n. The n makes things want to get large, but the 1 over n makes things want to get small. So it's the limit as n goes to infinity of 1 over n to the 1 over n. So one thing is to try certain numbers and try to get a feeling of what's going on. If I take maybe n to be powers of 2, what you'll quickly see is that this number is going to seem to converge very quickly to 1. And if you think about it, take a number like 100. Take 100 to the 1 over 100. Well, if I take the square root of 100, what am I at? 10. The square root of 10? Around 3. Square root of 3? Around 1.7. So that's just taking the 8th root of a number. The 8th root of 100 is already getting me down to about 1.7. I've got to take the 100th root. So it seems reasonable to believe that this would be getting very small. How could we attack this? We need to know, we have to study the limit as n goes to infinity of n to the 1 over n. And this is the same as the limit as n goes to infinity of e to the 1 over n log n. So this is a great way to attack problems like this. I can always use the exponential function. So if you're not sure how this works, let's say I want to find n to the 1 over n equals e to the x. So if I want to solve for x, what should I do to both sides? So if I want to find x, what should I do to both sides? Take the log. So take log, and we get the log of n to the 1 over n. That might be the most 1's and l's and n's you'll ever see consecutive, is the log of e to the x. Well, the log of something to a power is that power times the log, and so I get 1 over n log of n is equal to x. So what we can see is trying to figure out what happens to this quantity is the same as understanding what happens to this, is the same now as understanding what happens to the log of n over n. Which goes faster, log of n or n? So which will go faster? N. So take some numbers, take n equals 10 to the 10, well then the log, or I guess we're doing things base e, so if I do, for example, n equals e to the 100, the log of n is just 100. If I take n is e to the 1,000, the log of n is just 1,000. Log is growing much slower than n. How could I prove this rigorously? What could I use to study log of n over n? So what do I have that would allow me to study log of n over n? I've got infinity over infinity. Yes? Close enough. Alright, so L'Hopital. It's a verb, okay? L'Hopital the expression, right? I've got infinity over infinity. This is a natural case for L'Hopital. So I now have the limit as n goes to infinity of the log of n over n is the limit as n goes to infinity. The derivative of n is 1. What's the derivative of log? 1 over n. And this limit is just 0. So now we just have to trace everything backwards. This limit is 0. So that means we plug over here, we have e to the 0. Uh-oh, what's e to the 0? 1. Right. Limit of 1 over n to the 1 over n equals 1. Yet again, 1 over n has survived all of our tests. Okay. It's truly pesky. Okay. What's another series we could try where we have an idea of whether or not things work? So we just did the harmonic. What else do we know that converges or diverges? Geometric. So I'm not going to do the calculation. I want you to just go through and try an equals r to the n. The rth root of r to the n is not too bad. What's the rth root of r to the n? I'm sorry, the 1 over nth root, sorry, I'm on a lot of medication today. The 1 over nth root of r to the n. So I take r to the n, and I take the 1 over nth root of that. So the next example would be r to the n, and that's just r. So I'll leave that as an exercise for you to go through and see that the root test provides the same answers you would expect for the geometric series.
Sorry, I just missed once we found that we're going down to 0.
Right.
How did we then know the?
Well, because we had the limit of e to the 1 over n log n. And so this quantity is approaching 0. So this quantity is approaching e to the 0.
Okay.
And if it's approaching e to the 0, it's approaching 1. So unfortunately, there is no useful information. Right? So it's time for the integral test. Right? Finally, we will have a test that will allow us to figure out whether or not 1 over n, whether or not that series converges or diverges. Okay? Any questions on the root test before I erase it? So the difficulty here is you've got to be able to do the algebra. But again, like the ratio test, it's automatic. Okay. So now, the integral test. The integral test is extremely nice. Not only will we be able to find out if certain series converge or diverge, but we can actually approximate them. And depending on how much work, we can approximate them very well. And so what I want to do is I want to concentrate on, let's keep it as general as possible, as long as possible, and then at the end of the day, we will switch to the series 1 over n. So, assume we have a non-increasing or non-decreasing series, sequence, a sub n. So this means that each term is either at least as large as the previous or not larger than the previous. They could be the same. I could have a couple of terms that are the same and then get smaller for a while, then get smaller for a while. Or I could have a couple of terms that are the same, then it gets larger, then it gets larger. The integral test becomes a way to figure out approximately how big is the sum and whether or not the sum converges or diverges. In one of these cases, I claim it's very easy to figure out if the sum converges or diverges. Which is the case where it's easy to figure out if it converges or diverges? The corresponding series. If I have a increasing or a decreasing sequence.
If it's increasing, it's diverging.
If it's increasing, it's divergent. The only possible way I would have a convergent, non-decreasing sequence is if every term is 0. I'm not going to give you a sequence where every term is 0 and ask you, does this converge or diverge? Okay? So, later on, we can actually apply what we're doing to estimate sums of increasing terms. But if you just cared about whether or not it converges or diverges, you would never use the integral test. The terms aren't tending to 0, can't converge. So now, assume an is non-increasing. Okay? Assume we have a function f of x that is non-increasing and f of n equals an. Then the first part of the integral test is the sum, n goes from 1 to infinity, of an converges if and only if the integral from 1 to infinity of f of x dx is less than infinity. So to figure out whether or not the series converges or diverges, all we have to do is look at the corresponding integral and see is the integral finite. So there's two parts to the integral test. One part is actually doing the calculus. Right? We're going to have to do an integral. Fortunately, it's a calc 1, calc 2 integral. What's the difficult part of the integral test? Yes?
How do you tell if it's less than infinity?
So that's doing the integral.
Okay.
So that's one part of it. Is, can we show that this integral is finite? But what's the other difficulty?
Do I have to evaluate it at infinity?
What do you mean by evaluate it?
Like when you take...
So we have to do it. We have to do an improper integral. So we have to maybe integrate from 1 to m and let m go to infinity. But there's something else that's hard. This is very different than the root test. It's very different than the ratio test. It's more like which test? We only have one other test, really.
Comparative.
So what's difficult about the comparison test?
It does something to compare to.
You have to have something to compare to. So what is the difficulty here?
You have to find the function f.
You have to find the function f. Fortunately, most of the time there's a really good way to find the function f. Take your sequence an and replace every n with an x. All right, if I give you the word log x or ln x, don't replace the n in the name with an x. Replace every time you have an n with an x, and usually that works. So, hard part is finding f. Usually, replace n with x works. So for example, if an equals 1 over n, what should we take for f of x? 1 over x. If an is 1 over n log n, we would take f of x I'm sorry? 1 over x log x. And again, this is not a proof that this will work, but these are very natural candidates to try. And in all the problems you look at, this is the level that you'll need to try to figure out what to test. Alright, so let's try to think why the integral test should be true. So the integral test is saying that if I have a non-increasing sequence, whether or not it converges or diverges is going to be related to whether or not this function has a finite or an infinite integral. Well, let's think about what's going on. The function is non-increasing, the sequence is non-increasing. So, let's look at what's going on from n to n plus 1. I know my function equals an over here. And my function has to equal an plus 1 over here. Could my function go up and then come down? No. Could it undershoot an and come back up? No. It's got to go in some path like this. It's never going up. So when I'm trying to think of what's the area under the curve, f of x, it's basically going back to the Riemann sums. And so, if I want to draw the contribution from an, notice that the width of this box is 1. What is the area of this rectangle? So what would the area of that rectangle be? an plus 1. So this has area an plus 1. So if I look at the area under the curve, that's going to be a little bit more than this. And I may be off by that very first term. Because notice here, I'm not including the an term. And if I go all the way back, maybe I'm missing the a1 term. Is that going to affect whether or not the series converges or diverges? No, it's just going to shift the value by 1. I could also look at it the other way around. I could draw it this way. If I do it this way, what's the area in the big box?
an.
an. And now the integral is less than that. So what I'm going to be able to do is I'll be able to sandwich my series with the integrals on both sides, or sandwich the integral with the series on both sides, up to maybe a mistake on the last term or the first term. But that's not going to affect whether or not things converge or diverge. So this is just the rough sketch. I'm going to draw it very carefully now. But I just want to give you an idea of what's going on. It's very similar to the Riemann sums. I'm trying to figure out how much are we missing by. And it's going to be at most by one term. All right, so let's draw it very carefully now. And so what I'm going to do is I will do it for the specific proof by example. You know, you're not supposed to do this, but let's do it. Let's let an be 1 over n. So again, it doesn't really matter that I'm doing the sequence 1 over n. This is just for definiteness to keep the notation as light as possible. So here's 1, 2, 3, 4, 5. And then here's 0, we'll stay away from 0. Here's 1. And then 2 would be at 1/2. 3 would be at 1/3. 4 would be at 1/4. 5 would be at 1/5. And let's look and see what's the sum of the first 5 terms. The arguments are very similar. Do you want me to do the argument where we overestimate or underestimate?
Underestimate.
Underestimate. Loudest first voice wins. Okay. General philosophy in life. So we want to underestimate. So what I'm going to do is this box over here that has area A1. This box over here has area A2. This box over here has area A3. This box over here has area A4. This box over here has area A5. I'm sorry. Now here's my function. And now I can look at the area under the curve. Where do I not want to integrate from? So I've got to be a little bit careful in the integration.
0.
Yeah, things are blowing up at 0. So I can just tack on this box A1. Okay? I could also, instead of going in this direction, I could go in this direction. And if I write A1 over here, I mean this whole rectangle here has area A1. Over here, this whole rectangle here would be A2. This whole rectangle here would be A3. This whole rectangle here would be A4. So let's see what we would get. If I integrate the function from 1 to 5, f of x dx. Or actually, let me center it a little bit. So we want to integrate from 1 to 5, f of x dx. So we said we wanted to underestimate. So if we look at it, A1 plus A2 plus A3 plus A4 is going to be larger than this. So this would be less than equal to the sum, n goes from 1 to 4 of an. What will it overestimate? Yes?
Sum from n equals 1 to 5.
Not quite. Almost. Not from 1 to 5. To be very careful.
2 to 5.
2 to 5. So if I look at the sum, you know, A2 plus A3 plus A4 plus A5, that's less than the integral. So I've sandwiched this, n goes from 2 to 5 of a n. If you look at this, it's a little bit sad. Right? Here I've got 2 to 5, here I've got 1 to 4. I have different bounds for my sums. In the limit, does that really matter? Is it going to affect whether or not the series converges or diverges? No. And so I could try to make things a little bit better. If I added A1 over here, and I added A1 over here, and I added A1 over here, that'd be great, but then I would have double counted A1. Well, let's just do that, and we'll play some algebra games. So we get add A1, and we'll get the sum, n goes from 1 to 5 of an is less than equal to a1 plus the integral from 1 to 5 f of x dx is less than or equal to the sum, n goes from 1 to 4 of an plus a1. I don't want to have an extra a1. What do I want to have? What would I have loved to have there rather than an a1? Yes? I'd rather have an a5. Can I just replace the a1 with an a5? No, what can I do? I'm sorry? I could add a5 to both sides, or I could add 0. I could add a5 and subtract a5. And then I would get the sum, n goes from 1 to 5 of an, is thus equal to a1 plus the integral from 1 to 5 of f of x dx is thus equal to the sum, n goes from 1 to 5 of an plus a1 minus a5. So this will tell you how close this sum is to the integral. So this is extremely powerful. And I can control my error basically by the first term and the last term of my series. Well, if you think about it, if you go back to this picture, if I'm looking at the area under the curve, here's a2 plus a3 plus a4 plus a5. I've missed all of a1. So it makes sense that the value of the sum up to here is going to be off by at most a1. Probably a little bit less because I've got these regions over here. Similarly, if I go in the other direction over here, I'm overestimating. And I can then figure out how much I'm overestimating by going back. So we can now approximate things. Is there anything special in this problem about the number 5? So let's replace 5 with a really large number like n. So imagine n is huge, like a million, a billion, a quadrillion, a googolplex. N is huge. Does this sum converge or diverge? So does the sum of 1 over n converge or diverge? I'm sorry? The sum of 1 over n. It diverges, right? We did this with, 1/3 plus 1/4 is at least 2/4. 1/5 plus 1/6 plus 1/7 plus 1/8 is at least 4/8, which is again a half. We had that very painful proof. We'll now see a much better proof with the integral test. But that sum is going to diverge. If it diverges, it's going off to infinity. Being off by 1, is that a big deal? No. And over here, I have 1 minus 1 over big N. That's going to be very small. So this is going to allow us to calculate the sum of 1 over n from n goes from 1 to big N to within 1. That's pretty close. And again, we could do better, but so the sum, n goes from 1 to n of an is, a little n, is within 1 of the integral from 1 to n of 1 over x dx. What's the integral of 1 over x dx? What function is derivative of 1 over x? Yes? Natural log of x. And then I evaluate this at 1 and n, so I get the natural log of n. So, if I sum the first big N terms of the harmonic series, it is the natural log of n up to an error that's at most 1. We can do better than this if we wanted to. We can do a more careful analysis of what's going on, and there's a huge theory devoted to stuff like this. But this is the power of the integral test. So I think I gave you a homework problem where I wanted you to know how many terms do you need before the harmonic series, its partial sum is at least 1 million. Give you some problem like this. You can now really figure that out from something like this. Okay? It's extremely accurate. So we now know the sum of 1 over n diverges. Okay? Therefore, the sum, n goes from 1 to infinity, of 1 over n diverges. And not only do we know that it diverges, we have some idea of how rapidly it diverges. Okay? Any questions on what we've done so far? Yes?
How does getting ln of n show that it diverges?
Because as big N goes to infinity, what's the natural log of big N? That's going to go to infinity. So we know that the sum of 1 over n diverges. So this is the integral test. This sum is at most a1 plus this integral, which is at most this sum plus a1 minus an. Well, a1 minus an is at most a1. So if this integral is going off to infinity, the only way this can go off to infinity is if the sum goes off to infinity. Similarly, if the sum goes off to infinity, the integral goes off to infinity. If the sum is finite, the integral is finite. It goes both ways. So if you want to just figure out, does the series converge? Does the series diverge? If you can evaluate the integral, and if you can take the limit as big N goes to infinity, you're done. This is now the advantage of being at the blackboard. Let's change things a little bit. I'm going to change this, and I'm going to put a P over here. So what we'll do now is we'll now say, here. I'll move to over here. Consider an equals 1 over n to the p. So we'll try f of x equals 1 over x to the p. We might as well assume, if we want to, that p is greater than 1. Because we already know it diverges when p equals 1, we just proved that. And if p is less than 1, it diverges by what test? Yes?
Ratio test?
No, ratio test will give no information, unfortunately. So if p is less than 1, why does it diverge? What test? So this is going to be the comparison test. If p is less than 1, 1 over square root of n is greater than 1 over n. So since 1 over n diverges, 1 over square root of n diverges. So your comparison test would work here. So now let's study the integral from 1 to infinity of 1 over x to the p dx, or perhaps a friendlier way to write it is x to the negative p dx. How do we integrate this? What's the integral of x to the negative p? It's been a while since we've done integrals like this.
X to the negative p plus 1 over negative p plus 1.
Okay, so this equals x to the, of it is 1 minus p over 1 minus p. Evaluated 1 in infinity if p does not equal 1. If p equals 1, I'm dividing by 0. I then have to use the antiderivative of 1 over x is the natural log of x. Fortunately, we just handled that case. Alright, so now we get, when x equals infinity, we'll get infinity to the 1 over p, infinity to the 1 minus p over 1 minus p minus 1 over 1 minus p. Right? This part is no problem. What about infinity to the 1 minus p? When is this infinite? When is this finite? So for what values of p is this infinite? For what values of p is this finite?
So if infinity to the power of 0, is it still 1, or is it?
We don't like to talk about that in public.
Okay.
So we avoid that in public. You know, close the doors, pull down the curtains, you can talk about something like that, but for the most part, we want to avoid that situation. And in fact, that situation is precisely when p equals 1, which we've handled separately.
Right.
So somebody give me a value of p that's not 1.
0.
0. Okay, so now I would have infinity to the 1. Does that blow up, or is that finite? It blows up. So in fact, if you take any p less than 1, you get infinity. What if I take p greater than 1?
0.
It's going to be 0. For instance, if I take p equals 2, I get infinity to the negative 1. 1 over infinity, which is 0. So this is finite if p is greater than 1, and infinite if p is less than 1. So this allows us to extend our knowledge. So now we know that this sum converges if p is greater than 1, and it diverges if p is less than or equal to 1. And again, we handled the case when p equals 1 earlier. Okay. Any questions about this? Everybody happy with the integral test? Okay, I want to do one more example of the integral test as to why I like it so much. I'm going to give you a series, and I want you to first tell me if it converges or diverges. So let's do an equals n factorial. Converges or diverges? Diverges, right? This diverges violently. N minus 1 dot to dot 3 times 2 times 1. Alright, so we know it diverges. The question is how rapidly? If I give you n equals 100, approximately how big is 100 factorial? Most calculators, I think, will blow up if you try to put in 100 factorial. Or at least I know when I was a kid, around somewhere in the 60s and somewhere between the 60s and 80s was about how far the calculators were programmed to handle. But there are lots of times when we want something like this. Why might we care about evaluating n factorial? Anybody have any idea why we might care about this? Where have we seen?
It's related to the exponential function series.
It's related to e, so it gives you some idea of how quickly these terms are going to become insignificant. So when we do Taylor series, it will tell us, in fact, that these higher order terms really don't matter. And I'll show some movies on Monday that just 4 or 5 terms is enough to estimate signs so well you really won't tell the difference. So what is in Taylor series? Another is probability and combinatorics. N factorial is the number of ways to order n people when things matter. In a lot of things in number theory and probability and combinatorics, you have these factorials coming into play. And you want to know roughly how big they are. So the key fact is Stirling's formula. N factorial is approximately n to the n, e to the minus n, square root of 2 pi n. That gives you a rough idea of how big n to the n factorial is. I'm going to show you how to get very close to that, and I'm not going to worry about dotting all the i's. I just want to give you a general flavor to show you how the integral test can give you information like this. Well, if I'm using the integral test, what am I supposed to be using it on? I'm sorry? I need a function, and this is to figure out what? The integral test is applied to a series. I don't have a series. I just have a product. And I want to know what happens as I take more and more factors. Do you know any way to convert a product to a sum? How can you make a product a sum? Logs. So you should have a Pavlovian response for the rest of your life whenever you see a product. Resist the temptation if you're talking to, say, a 10-year-old on how they do multiplication tables. But when you're in advanced math, physics, science, whenever you see a product, think logarithms. Logarithms convert products to sums. Have you had lots of experience adding things?
Mm-hmm.
Yes, you're very good at that. Have you had lots of experience doing lots of multiplications? Huge numbers of multiples. We have Riemann sums. We don't have Riemann products. Right? We have a lot more experience with sums than we do with products. We have all the stuff we've just developed about whether or not a sum converges. You can apply this to products. There's another point in this semester where we actually applied products to expand the reach of something. Anybody remember where we used products? We'd originally developed something. So this was the theory of least squares. We had this beautiful, Kepler's third law, which was relating the period, how long it takes to go around, to the length of the semi-major axis. And the problem is the method of least squares, you needed to be linear in the unknown parameters. Well, if we did this log-log change of variables, we actually got new relations that were linear. So, again, you may have had sadistic teachers, in your elementary schools, junior high schools, but there was a reason to learn logarithms, whether or not they conveyed that to you. Right? This is where we get the dividends. Logarithms are extremely useful. They allow us to convert from the formulations that arise in certain cases to something we can understand. Let's let Bn equal the log of An, which is going to be the log of 1 plus the log of 2 plus the log of n. Actually, there's a better name to use than Bn. I should call it, not An. An is already plain. I should call it Sn for my partial sums. Right? So here, if I want to figure out how big An is, if I want to figure out how big n factorial is, if I can figure out how big Sn is, all I have to do is exponentiate. So this is a key idea. Take what you want to study, take the logarithm, study it, and then exponentiate. We did this earlier today when we were looking at n to the 1 over n. We took n to the 1 over n, we wrote it as e to the 1 over n log n. We then understood n, 1 over n log n, exponentiated, got back to where we want it to be. So over here, I want to figure out, what can I say about the sum? So what should I take for my function f of x? Log x. And so now we get the sum, n goes from 1 to n, of log of n is less than or equal to a1. What's a1? Log of 1 is?
0.
0. Right? 0 plus the integral from 1 to n of log of x dx. And that's less than or equal to the sum, n goes from 1 to big N of an plus 0 minus an. And an is going to be log of n. So all we have to do now is figure out what is the integral of log of x. Anybody remember the antiderivative of log of x? That's right. See, I think we have about 6 minutes left. Yes. Right. So what I will do is I will explain to you how you can kind of guess. So again, this was an issue that was raised earlier. The difficulty with the integral test is you have to be able to do the integrals. Now, you can at least prove that this diverges. Because, once x is at least 2, or once x is at least 3, all of these are at least log of 3, which is positive. Well, great. We already knew it diverged. We want to try to estimate how big the log of n factorial is. I claim the integral of the log of x dx is x log x minus x. If you doubt me, what can you do? Take the derivative. Okay, so you take the derivative and you see it works out. So the question is, how do you get something like this? Well, I want a function whose derivative is log of x. I could try maybe log squared x. But its derivative would be 2 log of x times 1 over x. Right? And that's going to be messy. I could try to fix things by maybe multiplying by an x here, and then use some kind of product rule, but it's going to be a little bit messy because I have this log of x. Another attempt is to try x log x. And the reason this is a good thing to try is when I take the derivative of x, I get log x, which is exactly what I want. And when I take the derivative of log of x, I get a 1 over x, which is going to cancel or reinforce nicely with the x. So its derivative is going to be 1 times log of x plus x times 1 over x. So unfortunately, its derivative is not log of x. It's the log of x plus 1. So I have to subtract something from this that has derivative 1. What has derivative 1? X. So now we try x log x minus x, and now when we take the derivative, we'll get log of x plus 1 minus 1 log of x. Okay? So we get the sum, n goes from 1 to n of the log of n, which is big N factorial, is approximately x log x minus x, all evaluated at 1 and n. So this is going to be n log n minus n minus, now when I put in 1, the log of 1 is 0. So I get a minus and a minus 1 over here. So I get n log n minus n minus n plus 1. Right. And so now we have, oh sorry, this is not n factorial, this is the log of n factorial. So we get the log of n factorial is about n log n minus n plus 1. So what do I do? Exponentiate. And so this is just a good way to just review some algebra. So now I get n factorial is about e to the n log n minus n plus 1. This is e to the n log n, e to the minus n, and then an e. Alright? What is e to the n log n? What's the first piece? So e to the n log n, what would that piece be? So let me write this as e to the log of n to the nth power, e to the minus n times e. Because again, if I have an exponential of a product, this is what it means. What is e raised to the natural log of n? N. The natural log of n is how many powers of e I need to get n. I raise e by the number of powers of e I need to get n. And so I get n to the n, e to the minus n, times e. That's pretty close to Stirling's formula. And again, right now I'm not worrying about am I over or under by a little bit. With more work, you can get that extra square root of n that comes in. But we're pretty close to the right order of magnitude. We're really accurate in our estimate of the sum of n factorial. I'm sorry, of n factorial as to what does that equal. So this is a really good place to stop for our units on sequences and series. On Monday we will do Taylor series. But what I hope you got from all of this is the difficulties of using these tests, which tests are better in which situations, and what information can you extract from the tests. So if you can remember that you can take logarithms, you can actually get a lot of good stuff. Okay. So we will finish class half a minute early.